Hi everyone, welcome to our first tutorial for SPPH 400. My name is Mary Claire Kennedy. In this tutorial, we're going to be reviewing graphical displays, diagnostic and screening tests, the difference between a sample and a population, Z-scores, and we'll also introduce the concept of the normal distribution. So this will likely be a review for most of you, but I'm just going to quickly go over the distinctions between different types of variables and how you can numerically or graphically display these. So in this course, we're going to be dealing with both univariate and bivariate data. So univariate means that we're dealing with one variable, so for example, an example variable of weight, while bivariate means that we're talking about the relationship between two variables. So for example, the association between weight and height. And there are different ways you can display univariate and bivariate data depending on the types of variables that you're dealing with. So I'll start with univariate. So variables can either be qualitative, so these are also known as categorical variables. So for example, women versus men, or variables can be quantitative, also known as numeric variables. So these indicate how much or how many. So for example, weight. So some variables can be either qualitative or quantitative depending on how we define them. So for example, with weight, we could use per pound increase, or we could categorize this into overweight versus not overweight. So I'll quickly review the different types of qualitative and quantitative variables, but this is all in Module 1. So first, let's start with qualitative variables. So these have different scales of measurement. So these can be nominal with no natural ordering. So for example, variables like gender or marital status, or these can be ordinal. So categories that have a natural ordering, but the intervals between each level are not equal. So for example, a variable that had strongly disagree, disagree, agree, or strongly agree, or something like first, second, and third in a race. Quantitative variables also have different scales of measurement. So these can be interval, where there are equal intervals between each level, but no absolute zero. So one example is temperature. So if you compare 40 degrees to 20 degrees, there's a 20-degree difference, but it doesn't make sense to say that 40 degrees is twice as hot as 20 degrees. And while temperature does have 0 degrees, this is arbitrary, so it doesn't mean there's a complete lack of temperature. Other quantitative variables are measured on the ratio scale. So with ratio variables, there are equal intervals between each level with an absolute 0. So for example, you can have a weight or a height of 0. And most quantitative data is on the ratio scale. And quantitative variables can also be discrete or continuous. So discrete means that they can take on a countable value. So for example, the number of people in your class. So this can only be counted as 1, 2, 3, or 4. You can't have half a person. But conversely, with continuous variables, these can take on any value. So for example, your age could be 32 and a half years. If you have a qualitative variable, you can display the data for this variable using things like pie charts, bar plots, and frequency distributions, all of which are shown here. You can display data for quantitative variables in a lot of different ways. So for example, you could use a histogram, a box plot, a grouped frequency distribution, a dot plot, or a stem and leaf plot. And most of this is explained in Module 1, but when you're asked on an exam or on your assignments, you should feel comfortable in identifying what type of variable it is and what graphical or numerical displays could be used for that variable. We can also use different graphical or numerical displays to examine bivariate data. So these are just examples, but if we want to examine the relationship between two qualitative variables, we can use things like mosaic plots, contingency tables, and side-by-side bar plots. So I won't go into detail about these today, but we'll learn later in the course about how we can analyze the relationship between two qualitative variables using methods like the chi-square test, Fisher's exact tests, odds ratios, and relative risk or rate ratios. If we want to summarize the relationship between two quantitative variables, we can use a two-way scatter plot like the one shown here. And later in the course, we'll talk about how we can analyze the relationship between two quantitative variables using correlation and simple linear regression. And finally, if we want to summarize the relationship between one quantitative and one qualitative variable, we can use side-by-side box plots. And later in the course, we'll learn about how we can analyze the relationship between one quantitative and one qualitative variable using methods like the two-sample t-test and ANOVA. So now we'll turn to a discussion of diagnostic or screening tests and how we can determine their discriminative and predictive properties. So most of you will know what prevalence is. It's the proportion of the population who have a disease. So 1 in 100 have the disease, or 1%. The sensitivity of a test is the probability that a person tests positive given that they actually do have the disease. So for example, the probability that a person tests positive for HIV given that they actually have HIV. The specificity of a test is the probability that a person tests negative given that they don't have the disease. So for example, the probability that a person tests negative for HIV given that they don't have HIV. The false positive probability is the probability that a person tests positive when they do not actually have the disease. So this is the complement of specificity. So if specificity is 0.6 or 60%, the false positive value is 0.4 or 40%. So it's 1 minus the specificity. The probability of a false negative is the probability that a person tests negative when they actually do have the disease. So this is the complement to sensitivity, so 1 minus sensitivity. The positive predictive value is the probability that you actually have the disease given that you test positive for it. So if someone tests positive for HIV, how confident can we be that he or she actually has it? With the negative predictive value, this is the probability that you don't have the disease given that you tested negative for it. So if someone tests negative for HIV, how confident can we be that he or she doesn't have it? So notice here that with positive predictive value and negative predictive value, the given is your test result, and we're rendering the probability of having or not having the disease or condition based on that result. But with sensitivity, specificity, false positive, and false negative, the given is your disease status, and we're determining the probability of your test result based on that disease status. So on the bottom right, you'll see alternative formulas for calculating positive predictive value and negative predictive value on the basis of sensitivity, specificity, and prevalence. And you don't need to memorize these or understand the math behind these for this course. If you're curious, there is some information in the module notes and the Pagano text on this, but it's not required. The main thing is that you know when to use these formulas and how to use them. So I suggest that you try some practice questions with these and also include these on your midterm and final exam cheat sheet in case you need them. So now we'll just turn to an example problem. So 100 people were tested for some disease. Among the 30 people who have the disease, 20 people were correctly tested. 33 people who didn't have the disease tested positive for the disease. Calculate the prevalence of the disease, sensitivity, specificity, false positive, false negative, positive predictive value, and negative predictive value. So the first thing we should do in approaching a question like this is write out what we do know. So the easiest way to approach it, the next step is in this situation is to draw a 2x2 table with disease status on the top and test status on the left, and then fill in the information that we know. So we know that 100 people were tested for a disease, and 30 people have the disease, And of these 30 people, 20 were correctly tested as having the disease, and 33 people who didn't have the disease tested positive. So we then do the math to fill in the rest of our 2x2 table. And now that we have a complete 2x2 table, we can do our calculations. So the prevalence is given to us. It's the 30 people have the disease out of the 100 people, so 30%. Sensitivity is the probability that you test positive given that you have it. So 20 of the 30 people with the disease tested positive for that disease, so 66.7%. The specificity, 37 people tested negative out of the 70 people who don't have the disease, so 52.9%. With false positive, 33 people tested positive out of the 70 people who don't have the disease, so 47% approximately. With false negative, 10 of the 30 people who have the disease tested negative, or 33%. Of the 53 people who tested positive, 20 actually have the disease, so the positive predictive value is 37.7%. And the negative predictive value we determined by saying that 47 people of the 47 people who test negative, 37 don't have the disease, so approximately 78%. So again, notice here that with the positive predictive value and negative predictive value, our denominator is test status, whereas with sensitivity, specificity, false negative, and false positive, our denominator is disease status. Also note that we can determine the probability of a false positive by subtracting the specificity probability from 1 and vice versa. So 1 minus the specificity probability of 0.529 equals 0.471, the probability of a false positive. And we can also determine the probability of a false negative by subtracting the sensitivity from 1 and vice versa. So each of these respective probabilities adds up to 1, which means the percentages add up to 100%. So they're complementary values. Okay, so here's another example. Consider a diagnostic test for a disease. Suppose that a woman who has the disease will test positive 98% of the time, and a woman without the disease will test negative 97% of the time. Further, suppose that 5 out of every 1,000 women have the disease. If a woman tests positive for the disease, what is the probability that she actually has the disease? What is the term used for this probability? So what is this asking for? The given here is testing positive, and we're wondering what the probability that she actually has the disease. So this question's asking for the positive predictive value. So that answers our question B. So to answer question A, the first thing we should do is write out what we know. So we know that a woman who has the disease will test positive 98% of the time. So this is the sensitivity. And a woman who doesn't have the disease will test negative 97% of the time. So this is the specificity. And we know the prevalence is 5 out of 1,000 people, or 0.5%. So based on this information, we could make a 2x2 table to try to figure out this problem. But the easiest way to solve this problem is to just plug it into our alternative formula for positive predictive value, inserting the values for sensitivity, specificity, and prevalence. And if we do that, we get a probability of 0.141, or 14.1%. And so we can conclude that if a woman tests positive for the disease, there's a 14.1% probability that she has the disease. And we already said before that this is the positive predictive value. So just a quick review about the difference between a sample and a population. So a population contains all the people or units that you're interested in for your study. So for example, all nurses who work in hospitals in Vancouver. A sample is a subset of the population selected to represent the entire population. So for example, 200 nurses working in hospitals in Vancouver. Statistics are numerical characteristics obtained from the sample of data. So for example, the proportion of nurses in our sample who have had a workplace injury in the past year. This statistic is our best guess at the true value of workplace injuries for this population, which is known as the parameter. And most often we're working with statistics from a sample and are using these to make inferences about parameters, the true values in our population. But in this course, SPPH 400, we're going to be moving back and forth between samples and populations. So first we're going to start with populations in a situation where we assume that we know the entire truth for a population. And this is rarely ever the case, but it's useful to learn about how sample statistics behave when we know the entire truth before learning about the situation in which we do not know this. So this brings us to Z-scores. So a Z-score is a standardized score. So standardizing scores, or changing these to Z-scores, simply converts the group of data in our frequency distribution such that the mean is 0 and the standard deviation is 1. And so a Z-score tells us how far an observation is from its mean in terms of its standard deviation. So it converts an individual score into the number of standard deviations that score is from the mean. So in other words, it tells us how much an individual score deviates from the true mean in terms of the average deviation from that mean. So using an example, if I compare my height to the true height for individuals in a population, so let's say Canadian women, and calculate a Z-score of 1.2, this means that my height is 1.2 standard deviations above the mean height of Canadian women. The formula is shown here. It's an observation minus the true mean divided by the standard deviation. So use of a Z-score assumes that we know the entire truth about the population we are studying. So we know what the true mean is, and we know what the true standard deviation is in a population. And Z-scores are useful because they tell us if the data point is expected or unexpected. So for example, how much taller or shorter am I than the average height? And this is particularly useful in some situations, especially when a score by itself often doesn't tell us much. So for example, if we're told that we've obtained a score of 85 on a beauty test, this could be very good news if most people have a score of 50, but less so if most people have a score of 100. So in other words, a score is often more meaningful relative to the mean of the sample or the population. A positive Z-score means that an observation is above the mean, and a negative Z-score means that it's below the mean. And also Z-scores can be useful because they allow us to compare two scores from the same or different distributions. So let's turn to an example problem. Find the Z-scores corresponding to a raw score of 132 from a normal distribution with a mean of 100 and a standard deviation of 15. How do you interpret this? Okay, so the first thing we do is write out what we know. Our raw score is 132, our known mean is 100, and the standard deviation is 15. So we plug this information into our formula to calculate our Z-score, and the result is 2.13. And so our interpretation is that a score of 132 is 2.13 standard deviations above the mean. And there are also some good practice questions in the module notes if you want to practice some more of these types of questions. Okay, so let's talk a little bit about the normal distribution. So many types of data have a distribution that is bell-shaped and roughly symmetrical. And the normal distribution is appropriate for summarizing those. So some of the properties of the normal distribution are that it's bell-shaped, it's unimodal, meaning that it only has one point, and it is symmetric around the mean. The normal distribution is defined by two parameters, the mean and the standard deviation. The spread of the distribution is determined by the standard deviation that surrounds the mean score. The normal distribution can only be used for continuous variables like height or weight. the total area under the curve of the normal distribution is 100%, and the normal distribution is characterized by the 68, 95, 99.7 rule. And this means that approximately 68% of the data will be within plus or minus 1 standard deviation of the mean. 95% of the observations will be within plus or minus 2 standard deviations of the mean, and 99.7% of the observations will be within plus or minus 3 standard deviations of the mean. So if a sample of students has an IQ of 100 with a standard deviation of 10, then approximately 68% of students will have IQs between 90 and 110. Approximately 95% will have IQs between 80 and 120, and 99.7 will have IQs between 70 and 130. And this rule is also important because we know that only about 5% of values will be more than 2 standard deviations from the mean. And it's extremely rare that we'll observe a value that is more than 3 standard deviations away from its mean. Okay, so here's an example problem. The systolic blood pressure of women between 18 to 74 years old follows a normal distribution with a mean of 129 and a standard deviation of 19.8. What is the probability that a randomly selected woman has a systolic blood pressure above 180? And what is the probability that a randomly selected woman has a blood pressure between 85 and 180? So the first thing we do is write out the information we have, and we then plug this into our Z-score formula to get a Z-score of 2.58. So now we want to know the probability of selecting a woman with a blood pressure over 180, which we now know equals a Z-score of 2.58. So the next thing we do is turn to our Z-tables. So you can also use statistical software to do this, but you'll also need to learn how to use these Z-tables for this course. So that's what I'm going to focus on in this tutorial. So the first table shows the cumulative probability up to the Z-score. So we can see this in the illustration at the top. We then go to the Z-score of 2.58. And we can see that 0.9951 or 99.51% of scores in a normal distribution will be below 2.58. We can also infer from this that 0.49% of scores will be above 2.58. Or we can look at this second type of Z-score table that shows the percent above 2.58 or in the tails. So you can see this in the illustration shown at the top. And we can see that there are 0.0049 or 0.49% of scores in the tail above our score of 2.58. So in other words, 99.51% of scores will be below this score. So note that we derive the exact same information regardless of which of these two Z-tables we use. So approximately 99.5% of scores in a normal distribution will be below a Z-score of 2.58, and approximately 0.5% will be above this score. So returning to our question, we can conclude that the probability that a randomly selected woman has a systolic blood pressure above 180 is 0.49%. And we can also find the same answer with our previous Z-table. So a score of 2.58 equals 0.9951, meaning that 99.5% of scores in a normal distribution will be below 2.58. So we simply take this value and subtract it from 1 to get 0.49%. So this is the same answer we had when we used the other Z-table. So our next question is, what is the probability that a randomly selected woman has a blood pressure between 85 and 180? So we already know that approximately 0.5% of scores are above a blood pressure of 180, but now we'll also want to calculate the probability of having a blood pressure below 85 so that we can determine the probability that a randomly selected woman will have a blood pressure between these two values. So again, we write out what we know, and plug in our value of 85 into our z-score formula to calculate a z-score of negative 2.22. And then we look at our z-table and see that approximately 1.32% of scores in a normal distribution are below this point. So we now know that there is 0.49% of our distribution above a z-score of 2.58 and 1.32% in the tail below a z-score of negative 2.22. So we subtract the total of both of these values from 1, or 100% if you use percentages, since this is the total area in a normal distribution. And this gives us an answer of 98.19%. So the probability that a randomly selected woman has a blood pressure between 85 and 180 is 98.19%. And so that's it for this tutorial. For the next tutorial, we're going to continue with the normal distribution. We're going to introduce the central limit theorem and the sampling distribution.